Okay, 3.1, the nature of exponential growth. So what is exponential growth? It is a pattern of growth in which each term is multiplied by a constant amount, so greater than 1, to produce the next term. Okay, the graph increases at a constantly increasing rate. Okay, so the equation for exponential growth is this one right here. Okay, so this A is going to be the initial amount that you start with. Okay, and then B is the base. So that's like the growth factor. So this is the amount, this is the factor that your initial amount is being multiplied by each time. And then the N, the exponent here, is the number of compounding periods. So how many times it gets multiplied by that base amount. Okay, when we have like exponential growth graph, it's going to look something like this. Okay, the original is just the starting of 1. So the y-intercept is 0, 1. And then this one's growing, I believe, by a factor of 2. So the base here would be 2. Okay, so example 1, a flu virus is spreading among the students at Mathville High School. So initially, on day 0, and remember, time starts at 0, okay? 3 students become ill. So that would be like our starting amount, which is A. Each of these students passes the virus to 2 other students. Wow, this is so convenient during COVID times. Okay, who become ill on day 1. And then each of these 6 students passes it to 2 more students, and they become ill on day 2. Okay, so every single time, these students are passing to 2 other students each. Okay, so A says complete the table until day 5 and graph the relation on the grid. Then create an equation for the number of students falling ill after n days. So n days just means the general. Okay? And it does say the assumption is no one can be sick more than once. So we're going to start with 3 people. So we have person 1, person 2, and person 3. They both give it to 2 people. So times 2 would be 6. Each of these people give it to 2 people. So 6 times 2 is 12. Each of those 12 people, 7, 8, 9, 10, 11, 12, okay, gives it to 2 people. That's 24. Each of these people gives it to 2 people. That's 48. Okay, so in general, we're going to have, it starts with 3 people, it multiplies by 2 n number of times. Okay, so if we were to graph this, 0, 3, 1, 6, 2, 12, oh, 3, realize there was no 3 there, 3, 24, 4, 48, then I'll just do 5, 96. Okay, so this is going to be 3 and then 2 to the n. In this question, time starts at time equals 0. So the domain is not going to include any negative numbers. Okay, so from the chart, we can look, okay, how many students came ill on day 3? Well, 24. And what about on day 5? That's our 96. So is this relation a function? Explain why or why not. Okay, so vertical line graph tells me that this relation is a function. Okay, so yes, we can say it passes the vertical line test, okay? Or we can say, like, specifically, this is more mathematically, each x corresponds to 1y. Okay, now D asks, use your equation to determine the number of students who become ill on day 12. Okay, so simply y equals, let me move this up, y equals 3 2 to the 12. So 2 to the 12 and then times 3, I get 12,288. Okay, since this is a word problem, we can say, therefore, on day 12, 12,288 people become ill. Okay, if the student population at Mathville High School is just 1,852, how long will it take the virus to spread throughout the entire school? Okay, so this would be our y value, right? This would be the number of people. So using the equation, 1852 equals 3 times 2 to the n. What I would do is I would divide both sides by 3, and then we're going to learn this formally later, but I will show you. So we get 617 and a third equals 2 to the n. Okay, so in a couple lessons, what we're going to do is we have to kind of trial and error this. So 2 to the what number equals 617. Okay, so you just go into your calculator. I put in 5, it's only 32. So I'll tell you what I'm doing. 2 to the 5 is only 32, so increase. 2 to the 8 is 256, so I need to increase. I need to get up to 517. Okay, 2 to the 9 is 512. So I know that I'm going to have to go a little bit higher than that. 9.5, 9.4, 9.3. I'm going to go to 2 decimals, 2.8. 9.27. So 2 to the 9.27 equals that 617. So after 9 days, so on the 10th day, it would have spread throughout the entire school. Okay, therefore, by the 10th day, it would spread to the entire school. Okay, now describe the pattern of finite differences for this relationship. Okay, so we've done this in grade 9 for lines and grade 10 for parabolas. So now we're going to do first differences for the exponential function. Okay, so as a review, we're going to go up the y column, and we're going to go 96 minus 48. What do we get? 48. 48 minus 24. What do we get? 24. 24 minus 12. We get 12. 12 minus 6. We get 6. 6 minus 3. We get 3. Okay, doesn't really seem like we're getting anywhere. Let's try second differences. Okay, so we know that it's not a line. 48 minus 24. We get 24. 24 minus 12. We get 12. 12 minus 6, we get 6, and then 6 minus 3, we get 3. Okay, so obviously it's not a line, and obviously it's not a quadratic. Okay, so we have something different for exponential functions. What we have is we have ratios. Okay, remember we're multiplying by 2 each time, so check this out. We're going to go up the y column, but this time we're going to divide. So what's 96 divided by 48? 2. What's 48 divided by 24? 2. What's 24 divided by 12? 2. 12 divided by 6, 2, and 6 divided by 3, 2. Okay, we have the same ratios. So for finite differences, this type of table, exponential growth has a repeating pattern of finite differences. The ratios of the y values is constant. Okay, any number raised to the exponent 0 equals 1. Okay, so if we had like 4 to the 0, that would be 1. Negative 8 to the 0, that would be 1. Okay, if we had a decimal or a fraction, maybe 3 over 4 to the 0, again 1. Okay, so example 2, any non-zero real value is raised to the exponent 0 is equal to 1. So b to the 0, so b would be any real number except for 0. Like we can't have 0 to the 0. You'll learn that in university, but that we can't assess. So any b that's a real number raised to the 0 is 1. Okay, so if we have the equation y equals 5 to the x, what we're going to have is 1, and then we're going to have 5, 25, and 125. Okay, now what about 10? And then we're going to draw a conclusion from here. Okay, so if we plugged in 0 here, we'd get 1, but then times 10 is 10. And then if we plugged in 1, we would get 50. Then if we plugged in 2, so 5 squared, and I'm just double checking. 5 squared is 25 times 10, we get 250. And then 5 cubed, we get 1,250. So if we actually take a look at this, okay, our normal graph, no matter what the base is, our normal graph is always going to start at 0, 1. Unless there's this vertical stretch, right? So this would be a vertical stretch by a factor of 10. And what that would do is it would allow us to graph it. It's going to look like exactly the same. It's going to look like an exponential function going up to the right, but now our y-intercept is actually going to be located at 10. So 0, 10. Okay, and every one of these numbers is now, if you can see, it's all the y's are multiplied by 10. So example 3, a type of bacteria grows so that it triples in number every day. Okay, so triples, what does that mean? That means we're going to have a base of 3 because essentially it's going to times 3, some number times 3, so many times. Okay, Roger is growing a culture of these bacteria. He begins with an initial population of 10. Okay, initial population, we know that's our A. Okay, so find the population after each of the first 4 days. So the initial population is 10. Now, what's 10 times 3? 30. So we don't do 10 times 6. What we do is we take this 30 and we multiply this by 3. Okay, and we get 90. And now we start with this 90 and we multiply this number by 3 and we get 270. And we multiply this number by 3 and we get 810. The general form of our equation now is going to be y equals, it's not going to be y, it's going to do, we're going to have p, and we're going to have population p, okay? So even though they're not formally defined in the question, we have population at time t equals the starting number times the base, so times 3, times 3, times 3, t number of days. Okay, so we did A. Use the finite differences to prove that it's exponential. So let's do that. So 810 minus 270. So I'm just going to show you that when we subtract up the y column here, 30 minus 10, I get 20, 60, what is that, 180? 810 minus 270, okay, 540. So when we subtract up the y column, we do not get a constant for the first differences. When we subtract up the first differences column, we do not get a constant second difference. So it's not quadratic either. So 120 and then 540 minus 180, we get 460. Okay, so those two don't work. But now let's do the ratios. 810 over 270, we should get 3. 270 over 90, we should get 3. And look how convenient that is. What's our base again? 3. So this is really going to reflect your base. Okay, so therefore, it's exponential. Because these y values, the y ratios, are constant. Okay, so now let's graph this. So we're going to call this the p-axis, and this is population. Okay, and then this is time, and this is the number of days. Okay, so we're going to start at 0, 10, 130, 290. 130, 290, 3, 270. Okay, so that's off the chart. That's okay. Okay, and we're going to label this P at t equals 10 times 3 to the t. Is this relation a function? Yes. Each x corresponds to 1y. Okay, and it also passes the vertical line test. Okay, so E. Assuming that this trend continues, use your equation to predict the population after 1 week and 2 weeks. Okay, so be careful with these. 1 week is a weekly measure, but our tripling life, that's what we call it, like every single time we triple, it's a day. So 1 week converted into days is 7 days. 2 weeks converted into days is 14 days. So we're going to say, what's the population at 7 days? Okay, so 10 times 3 to the 7. When we put it in our calculators, we get 21,870. Now, what's the population at 14 days? So the population at 14 days is 10 times 3 to the 14. And we get 47, 829, 690.